Good morning, children. We have started a new lesson, lesson number 4, Effects of Electric Current of Science 1. And in our previous videos, we have learnt about energy transfer in an electric circuit and heating effects of electric current. So in today's video, we shall learn about magnetic effect of electric current. So let's begin. Magnetic effect of electric current. We have studied about two types of magnets. Those are permanent magnet and temporary magnet. Do you remember them? Yes. This is how one can define them in simple words. Permanent magnet retain their magnetism for a very long time, and temporary magnet retain their magnetism only for a short period of time or until kept under an external magnetic field. We will talk about temporary magnets first. Temporary magnet retain their magnetism only for a short time or until kept under an external magnetic field. When removed from the external magnetic field, they lose their magnetism. Got it, children? Now, we have seen two easy processes used to make a temporary magnet. We use objects made up of ferromagnetic material such as iron nail or an iron bar. What do we know about magnet? Yes, we know that magnets attract magnetic objects like iron attracts or repel other magnets. Do you know what is this property is called? This property of magnet to attract or repel is called magnetism. Look at these examples we saw. What is happening here is that the two objects acquiring magnetism to their processes. So, these objects weren't magnets. They acquired magnetism. This process through which any non-magnetic object acquires the property of magnetism is called magnetization. Yes, magnetization. This can also be defined as the process to magnetize any non-magnetic object. So, in these processes, we are magnetizing the ferromagnetic object. Now, there is one more way in which we can magnetize these objects, and that is by understanding that electric current generates magnetic field. Now, first, let's enlighten ourselves about this. In 1819, there was a scientist named Hans Christian Ørsted. He found out that if you keep a compass near a current-carrying wire, then the compass needle deflects to some extent. Yes, understand these words. when current passes through this wire and we keep this compass near the wire, the needle will deflect. This will not work if the current in the wire is feeble. However, in that case, if we remove some part of insulated coating and keep the compass in that region, you will see the deflection. Now, we know that the fact that if we keep this compass at rest away from any other magnet, then it will align itself in the direction of Earth's magnetic field. That is, the red part will point the north direction while the other part will point south direction. What will happen if we bring any magnet near this compass? Well, if we bring the north pole of the bar magnet near the red needle, the needle will show deflection. The needle now align itself to the direction of the magnetic field of this bar magnet. We know that in a bar magnet, the field line emerges from the north pole curve around the magnet and ends at the south pole. So if we move the compass in the direction of the magnetic field, then its needle will also align itself in the direction of the field. Keeping this knowledge in mind, let's go back to our copper wire. Here, the electric current in the wire produces magnetic field around the wire, or in other words, the wire becomes a temporary magnet. This is the reason that the compass needle deflects when brought near this wire. Understood, children? So the next we will start magnetic field around a straight conductor. Let's see. Magnetic field around a straight conductor can be understood by the following activity. Take a flat cardboard and cover it with a white sheet of paper. In the middle of the cardboard, make a hole through it. Pass a thick wire and connect the ends of the wire to a dry cell using connecting wires. Plot the magnetic lines of force around the conductor with the help of a plotting compass. It is observed that the lines of force are in the form of concentric circles. The direction of the lines of force will be clockwise. So, the experiment is repeated again, but now the current is passed in the opposite direction as shown in this figure. Then the lines of force will be in anti-clockwise direction. So the direction has changed now. If the strength of the current is increased, then the number of lines of force around the conductor also increases. This in turn increases the magnetic strength of the conductor. Understood, children? So, let's see the next one now. Magnetic field around a straight conductor. That is, we'll learn about right hand thumb rule. Now children, imagine that you are holding the conductor in the palm of your right hand such that the thumb points in the direction of the flow of current. Then the direction in which the fingers curl around the conductor gives the direction of magnetic lines of forces. Okay? So observe the given figure now. What you can see. Here the fingers are curling in an anti-clockwise direction while the thumb is pointing in the direction of the current. Yes? Therefore, the direction of magnetic lines of forces is in anti-clockwise direction. So this is the right hand thumb rule. Next we will study about magnetic field due to a current in a circular coil. Magnetic field due to a current in a circular coil can be understood by the following activity. Let's see what is the activity. Take a drawing board and fix a white paper sheet over it. Make two holes A and B in the drawing board and pass a thick copper coil through it. Connect the ends of the copper coil to a dry cell through a switch and a variable resistance. Close the circuit and plot magnetic lines of force with the help of a plotting needle. Okay, now let's see what happens. So, we can see that the magnetic lines of force around the hole A are in anti-clockwise direction. You can observe in this figure. However, the magnetic lines of force near the center of the coil becomes almost parallel. And around the hole at point B, the lines of forces are in clockwise direction. Can you observe your children? So, in the above activity, the lines of force enter the coil from the side of the experimenter, right? So, we can say that the force of the coil towards the experimenter acts like as a south pole and the face opposite to the experimenter acts as a north pole. Understood? Now, relate the above observation to the flow of current in the coil, and then we can say that if the current flows in the coil in the clockwise direction facing the experimenter, then that force of coil will act as south pole. Okay? And if the current flows in the coil in anti-clockwise direction facing the experimenter, then that face of coil will act as north pole. Understood, children? Very good. Let's see the next one. Magnetic field in a solenoid. So let's see what it is. Let us study first what is a solenoid. An insulated copper coil is wound around some cylindrical cardboard. Okay. Then, or a plastic tube such that the length of the coil is greater than its diameter. Then it behaves like a magnet when an electric current flows through it. So, this is called a solenoid. Understood now what is a solenoid? Okay. Look at the figure of a solenoid. When an electric current is made to flow through it, then each turn of the coil behaves like a magnet. In figure A, current is flowing into the coil in clockwise direction. So the left hand side of each turn of the coil acts as the south pole. Whereas the right hand side of each turn of the coil acts as the north pole. In figure B, current is flowing into the coil in anti-clockwise direction. So, the left hand side of each turn of the coil acts as north pole, whereas the right hand side of each turn of the coil acts as the south pole. Are you getting me, children? Thus, the situation becomes similar to a number of small bar magnets placed end to end with their opposite poles facing each other, such that they collectively act as a bar magnet. Thus, a solenoid behaves like a bar magnet. So, it is clear that if the number of turns in a solenoid increases, then the magnetic effect also increases. Isn't it? Yes. The magnetic field around the solenoid is similar to the magnetic field around a bar magnet. I hope I have cleared myself, children. So, let's look at the summary. Magnetic effect. When electric current is passed through a coil of insulated wire coiled around a soft iron bar, the iron bar behaves as a magnet. This is called magnetic effect of electric current. Magnetic effect disappears as the current stops to flow. Magnetic field and field lines. Magnetic field. The region around a magnet where the force of attraction or repulsion can be detected is called magnetic field. It is around a magnet and can be detected by using a magnetic compass. Magnetic field lines. Magnetic field lines are the part around a magnet along which the north pole of a magnetic compass needle tends to move. The magnetic field lines around a magnet can be observed by sprinkling iron filings around a magnet. It can also be observed by moving a magnetic compass around a magnet. So, the magnetic field lines emerge at North Pole and merge at South Pole. The magnetic field lines are closer at the poles, and the magnetic field lines do not intersect each other. You can see these in the figures given. Magnetic field due to current in a circular loop. When the current is passed through a circular conductor, the magnetic field produced is in the form of concentric circles around the conductor. Towards the center of the arcs of the circle becomes larger and appears as straight lines. Magnetic field due to current carrying conductor. If a magnetic compass is placed near a conductor carrying current, the needle is deflected. This shows that a conductor carrying current has a magnetic field around it. If the direction of the current is from north to south, the deflection of magnetic needle is towards the east. And if the direction of the current is from south to north, the deflection of the needle is towards the west. The magnetic field around a current carrying straight conductor is in concentric circles. It can be observed by passing a current carrying straight conductor through a cardboard and sprinkling iron filings in it. Now, what is right hand thumb rule? The direction of magnetic field around a conductor is given by right hand thumb rule, and it states that if a current carrying conductor is held in the right hand such that the thumb points in the direction of the current, then the fingers wrapped around the conductor shows the direction of magnetic field. Yes? Magnetic field due to current in a solenoid. A solenoid is a circular coil of wire in the shape of a cylinder. When current flows through a solenoid, it behaves like a bar magnet. The ends of the solenoid behaves like the north and south pole of a magnet. The magnetic field produced by a solenoid is similar to the magnetic field produced by the bar magnet. The strength of the magnetic field depends on the strength of the current and the number of turns of the coil. So children, I hope today's topic was interesting and everyone has understood the concept. Yes children? Do you find the lecture was interesting? I hope so. So, we shall see you in the next video with a new topic children. Till then, please do read the lesson and complete the given notes. Thank you children. Take care. Bye-bye.